We're going to look at two examples here of optimization. So the first example involves a garden here. So a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other three sides. Given 100 meters of wire fencing, determine the dimensions that would create a garden of maximum area. What's the maximum area? So if we've got a rock wall, we can consider this basically a free infinite size wall. But then we also have some fencing here that we're going to fence in with a rectangular. They said yes, a rectangular garden. So let's label these sides. I'm just going to call this A, and this B. So we want to find area. Well, we know area is going to equal A times B. The problem is we've got two variables now, so I can't very well take the derivative here. But we know that A plus B is equal to 100. In other words, B is equal to 100 minus 2A. And if you want to solve this for A instead of B, that's fine as well. But that lets me get A is equal to, capital A area is equal to lowercase a, and let's swap this to an x. X times 100 minus 2x, just so it looks a little more conventional. So then the derivative of area, because we're trying to find the maximum, is going to equal, we can use the product rule here, the derivative of the first term times the second, 100 minus 2x, plus the derivative of the first term times the derivative of the second, which is going to be negative 2. And we want this to equal 0, because that's where our critical points will be. So we're going to get 100 minus 4x. So we get 4x is equal to 100. X is equal to 25. We know that our endpoints, which is where either the fence is all in the A direction or the fence is all in the B direction, will produce areas of 0. So we'll ignore those, and we know it's probably our critical point. So if we plug X in, we get 25 times 100 minus 2 times 25, which will be 25 times 50, which is, what is that as a result? 1,250 feet squared. So that's what we're doing here. We're just basically finding derivatives, finding critical points, and then figuring out which of the critical points we want to work with. A second example is this box that's going to be made by this 24-inch by 36-inch piece of cardboard, cutting out a corner of cutting out a square from the corner of each of the box, and then folding up the flaps so they make sides. What size square should be cut out to get the maximum volume? Well, we know volume is equal to, and if we look at this diagram, it's going to equal to 24 minus 2x, because that's this side right here, times 36 minus 2x, because that's the other side, times x, because that's the height. If you expand this out, you get the function 4x cubed minus 120x squared plus 864x. I've done that before just to speed things up. Similarly, I've taken the derivative. V prime of x is going to equal 12x squared minus 240 plus 864. That should be 240x. Setting this equal to 0, we have to use the Pythagorean theorem because, the quote, I'm blanking on the name, quadratic formula, because this doesn't factor nicely. And you'll end up with two x values. X equals 10 plus or minus 2 square root 7. reverse that. So 2 plus or minus square root 7, which if you solve that out, that's 4.71 or 15.29. And if we look at our original diagram, 15.29 won't work because if I cut that much out, I'm going to cut out more than this long side actually has in it. So it's got to be our 4.71. So then we can take that, go back up to our original function, plug it in, and we get a volume of about 1,825 inches cubed as our maximum area. So in this case, we were able to tell on our, just by looking at these numbers, which one we wanted and which one we didn't want. If we weren't sure, we could plug both of them in and you would end up seeing that this one gives you a negative volume, which obviously cannot be right. Because negative volume in this context doesn't make sense. How would you have a box with negative volume? So that's our second example. If you have any questions, let me know.